talk a bit about normalization of closed linear lambda terms, and more generally about some patterns in terms and maps in the end. Okay. And so some of you might already have seen me talk about these things, so you might be bored during this talk. So I will give you a little bit of a quiz to think about in the meantime. So of the following types of radices, which one has the highest mean number of occurrences in random closed linear lambda terms? And so we talk about the highest mean number here asymptotically, right? So we take closed linear lambda terms of a big size, and we see asymptotically which one of these radices is the most common. So is it the case of abstractions applied to variables, the case of abstractions applied to abstractions, or the case of abstractions applied to applications? So this is a little bit of a quiz for you to think about if you're bored during the talk. Okay. And so to introduce now the two objects that we're going to work with, on one hand, we have maps. And so you saw them yesterday, perhaps during the talk of Wenji. So what are maps? Maps are embeddings of a graph. So you take a graph and you embed it in a surface. And so here for us, the surface will be either the sphere or the n torus. So the torus with n holes, right, of genus n. And so equivalently, because we are combinatoricians, we can think about this as just a graph for which, for every vertex, we have defined a cyclic orientation of the half edges incident to it, right? So a permutation around its vertex. And so these are very ubiquitous objects. They appear everywhere in mathematics and physics even. And so they are a central object, of course, in modern combinatorics, but they also appear in probability theory, where they appear in the study of scaling limits, of local limits, etc. In algebraic geometry, in theoretical physics, where they connect things like matrix integrals, proof of Windus conjecture, etc. And of course, in combinatorics, we have the four-color theorem, which famously is about maps, right? And so in terms of their enumeration, the first work was done by Dutt in the 60s, which was incidentally part of his approach to the four-color theorem. So on one hand, we had maps, and now we have the untyped linear lambda calculus. So what is the untyped linear lambda calculus? It is a system of computation whose terms are formed inductively using the following rules. So as usual, we have a rule for introducing variables. So we have here a context. So we can always have a free variable of the form x, where we keep it in a context here on the left-hand side, and we say it's a free variable. And so if you have, if you can derive some term t from a context gamma together with a variable, free variable x, then we can also derive the term lambda x dot t from the same context by deleting this free variable x. And so here we say we have the case of abstractions, where x is bound by this lambda, and these are supposed to represent functions which take some input x and execute whatever is written in their body t. And finally, of course, we have applications, which are of the form f applied to t. So if I can derive f and t separately, then I can, supposing that their contexts are disjoint, I can concatenate the context and derive the application term f applied to t. And so this represents the act of feeding an argument t to a function f, right? And this little calculus here comes together with two structural rules. The rule of exchange, which says that we can freely swap free variables inside their context. And the rule of contraction, which says that we can apply this little rule here of have gamma xy derives t, then we can also replace y with x inside t and drop y from our list of free variables. And so this gives us a system for the untyped linear lambda calculus. And so what is the connection between these two objects I have introduced? So the connection was first discovered perhaps in 2013 when Bodini, Gardy, and Jacob described a series of bijections between rooted trivalent maps and closed linear lambda terms, and a bit more generally between rooted two trivalent maps and closed affine terms. So trivalent maps are those that have the property that each vertex, except for the root, has degree 3, right? And two trivalent maps is the same thing, but we allow also for degree 2. And in the same year, together with Bernard, they study BCIP terms, which are a generalization of this linear lambda calculus, where its bound variable appears p times. And so in the linear lambda calculus, its bound variable appears exactly once, and here we have exactly p times. And more generally, they studied the general closed lambda terms. almost in parallel, we have in 2014 Zellberger and Giorgetti describing a bijection between rooted planar maps and normal planar lambda terms, which Wendy discussed a bit last time yesterday. And so the glue that holds these two together, the connecting pin, is the fact that they both make decompositions. They make use, of decompositions in the style of Tut. And so we can compare this with the approach of Arquet and Béraud in 2000, where they used a similar kind of Tut-style decomposition for enumerating maps of arbitrary genus. And so in 2015, Zellberg advocates for the viewpoint of linear lambda terms as invariants of rooted trivalent maps, which is this viewpoint that we'll adopt here. This shouldn't say thesis. I should have changed the slide. I did actually. Anyways. And so the working context, to put the working context a bit, we have related work that has been carried out on the parameter studies on general lambda terms. So people have looked into statistics for general lambda terms, but they have used different size notions, a number of size notions which do not agree with ours anyways. And they also have studied statistics in general maps, but our focus here will be on trivalent maps. So we will not look neither at general lambda terms nor at general maps. We look at trivalent maps, so cubic maps, and at linear terms and related families. And we'll explore the combinatorial interplay of these maps and terms, with the goal being to study pairs of parameters of maps and terms. So we'll see that we study statistics that naturally come in pairs, or of a statistic for lambda terms and a statistic for maps which are connected, right? And so some results in this area are, for example, pairs of statistics like loops in trivalent maps, so the number of loops in trivalent maps, and the number of identity subterms in closed linear terms, for which we have derived the Poisson-1 law. And this will come into play later on. More generally, bridges in trivalent maps and closed subterms in closed linear terms also have Poisson-1 limit law. And so this was work with Olivier Bodini and Noam Zellberger, and then with Bernard Gittenberger and Michel Wallner, we have studied some kinds of patterns in trivalent maps, which are connected with the number of radices in closed linear lambda terms. And for this, we have obtained an asymptotic mean and variance of n over 24. And finally, we have studied a lower bound for the number of steps to reach normal form for closed linear lambda terms, which is asymptotically 11n over 240. And so, as the title suggests, in this talk we'll focus on these last two bullets here. And what is our strategy for deriving these results? Our first step is always going to be to track the evolution of parameters in decompositions of maps and lambda terms. And we have a lot of decompositions here. We have decompositions based in some kind of a pointing process, in some kind of a cutting process, or just by linking vertices with half edges together. And so we have a bunch of different specifications for trivalent maps and lambda terms. And one of the tricks in this whole process is to find a good specification, one that allows you to track your statistic of interest. So once we have done that, once we have found a good decomposition, we have found a way to specify our desired generating functions, etc. We obtain some kind of a specification based on perhaps differential equations, Hadamard products, etc. And invariably, all of them, the solution, the generating function solution, the power series solution to this kind of equation that we're interested in is always some kind of generating function divergent away from zero. So here we are in a very non-analytic place. So we lose access to all the nice tools of analytic combinatorics like singularity analysis and saddle point theorems, etc. And so instead we have to develop new tools and expand existing tools to deal with rapidly growing coefficients. And so our tools will be based on moment pumping, on Bender's theorem for compositions of some convergent power series F with some divergent power series Z of Z. And finally, some kind of little lemma for dealing with coefficient asymptotics of Cauchy products. So when we have two divergent power series A of Z and B of Z multiplied together, we can extract their coefficient asymptotics by considering extremal cases where one part in a pair is huge, the other part in a pair is tiny, right? So using this kind of three general tools, lemmas, we can deal with the analysis of the divergence range functions we'll encounter here. Okay, so now to make the connection between closed linear lambda terms and trivalent maps a bit more concrete, I'll present to you a bijection between the two. And so starting from terms, to go to maps, it's quite easy. We essentially draw some kind of a diagram for the terms. And the diagram, the rules for the diagrams are as follows. If you have an abstraction lambda x dot t, we draw this little diagram here we have on the left, where we have a vertex labeled lambda with an outgoing wire, which represents the output of the function perhaps. And then we have an ingoing wire coming off from the left, which represents the bound variable x. And then we have a sub-diagram or a sub-map, which represents the body t. Similarly, for an application, if you have S applied to t, then we draw a vertex labeled A, whose sub-diagram on the left is t, and sub-diagram on the right is S. And so you can see here it's a bit, we have flipped a bit the orientation between S and T, and this is for convention, it's for traditional reasons anyways. And so in this convention, we draw S applied to T as S being on the right sub-diagram. Okay, so if we apply this, and of course we notice here that the order matters, right? S applied to T is not the same thing as T applied to S. And so of course, we have a diagram which is not only a graph, but it contains this kind of information we said before. It contains a cyclic orientation of the half edges incident to its vertex for every vertex labeled the lambda or alpha, right? And so this is, as we said, equivalent to specifying an embedding for our graph. And so indeed we obtain a map in the end, a map with some kind of labeling on its vertices. And so if we apply this kind of rules to the term we see here on the right, we obtain this diagram here. And so we can start by playing together with a term and a map. We can start to notice a number of correspondences between properties of the map and properties of the term. And so we can build a little dictionary of correspondences, like, for example, the number of subterms in a term corresponds to the number of edges in its corresponding map. And so it makes sense then to take the size of a map to be its number of edges when we enumerate maps by their size, and then the size of a term to be the number of subterms. And so this makes the two sequences align in terms of their indices. We can also notice some structural properties, like, for example, the existence of a closed subterm corresponding to the existence of a bridge in a map. And so, for example, if we have an identity function like the one we have here, lambda xx, it corresponds to a bridge with a loop on one of its sides. And if in more general terms we have a closed subterm like the one like lambda w, lambda u here, it corresponds to a proper, like a bridge with a proper block on the other side, right? Similarly, planarity of maps, as you saw yesterday during Wednesday's talk, planarity of map corresponds to planarity of the corresponding lambda term. And so we have a bunch of structural properties of maps corresponding to structural properties of lambda terms and vice versa. And so far I described to you an injection from lambda terms to maps, but a kind of decorated map, right? We saw that there are labels for its vertex, either lambda or alpha. And so here a question naturally arises of whether we can erase the labels and so obtain a proper map, an unlabeled map, right? Undecorated map. And the answer is yes, indeed, we can erase this label and recover them by an exploration process, which I described now for you. And so to describe this visitation process, decomposition process, I will show you how to decompose a rooted trivalent map first. And so a rooted trivalent map, as we said, is one that the root has degree 1 and every other vertex has degree 3. And so the smallest possible such map is the little loop we see here. And then we can consider what happens when we delete the root and its neighbor. If deleting them gives us a disconnected map, then of course we obtain a pair of disjoint maps, and we have this case here. Otherwise, if deleting them gives us a connected map, it means that we started with a map, we selected one of its edges, here colored in pink or purple, sorry, and then we split it, so we subdivided, we introduced a new vertex here, and then we linked this vertex to the root. And so this process of splitting an edge and connecting it to the former root is the same thing as it's exactly the unique way to obtain a map such that deleting the root vertex and its neighbor gives you a connected map, right? Because the neighbor of the root must be connected to something inside the body of the map. And so here we have a proper decomposition for rooted trivalent maps, but we can see here that this exactly mirrors the structure of closed linear lambda terms, where the smallest possible closed linear lambda term is the identity function lambda x dot x, whose diagram is this loop. And then S applied to T, as we said, is given by a diagram where we have two disjoint maps getting linked to the root. And finally, if you have lambda x dot T, by linearity, we have that the variable x bound by the outermost abstraction either appears on the left or on the right of an application. And so we have these two possible forms here on x dot T, where we have replaced u in T with x applied to u or u applied to x. And this corresponds exactly to this third case of cutting to the left or to the right inside the map. Okay, so now we have a proper bijection between rooted trivalent maps and closed linear lambda terms that we can use to enumerate our two objects, but also, of course, we can use it to study statistics on both objects at the same time. Now, the lambda calculus is not only the set of its terms, but it also comes equipped with a natural dynamics, right? A notion of computation, which is given by this rule of beta reduction. And so beta reduction says that if I have an abstraction lambda x dot T1 applied to T2, I beta reduce it to T1, where I replace all occurrences of x, free occurrences of x in T1 with T2. And so this represents roughly the idea that if I have a function which maps x to T1, then feeding T2 to the function is equivalent to replacing x inside the body of f with T2. And so this is a rule that says what happens when I feed a function, an argument to a function, right? And so an example of, so this little pattern we see here, lambda x dot T1 dot T2 is called a redex, so it's something reducible. And so an example of a reduction, we have here a redex of the form lambda x dot x applied to y. And so clearly we see here we have an identity function applied to some argument y. And so beta reducing gives us y back. And more generally, we can have a bunch of redices in our term. And so we can choose some order in which to eliminate them. And so we get a chain of beta reductions, which terminates hopefully with some term which contains no redices, like we have here. And so term with no redices is called the normal form. And for linear lambda terms, beta reduction is actually strongly normalizing and has the strong diamond property, which means that roughly beta normalization always terminates in a unique normal form, and it does so in a deterministic number of steps. In terms of maps, beta reduction looks like an unzipping process. We have here the beta reduction pattern, beta redex pattern in our maps, which is an application whose right side is a lambda. And so by unzipping, we get this kind of new trivalent map. And so here we have a little chain of beta reductions terminating in a map with no redices. Okay. So naturally, we have given the strong normalization and strong diamond properties, we naturally have a question of how many steps does it take for a random closed linear lambda term to reach normal form. And so a lower bound for this number of steps required to normalize a random closed linear lambda term is given by the number of its beta redices. And so naturally, we have a sub-question, a first lower bound of what is the number of beta redices in a random closed linear lambda term, where we take as our model for random terms the uniform distribution on terms of size n. And so why is this just a lower bound? It is so because it can happen that we reduce a redex and create a new one in its place, as we'll see later on. And so our first goal then is to track the mean number of beta redices in large closed lambda terms, linear lambda terms, right? And so tracking redices is easy. We'll go back to the decomposition. It starts off easy anyways. We'll go back to the decomposition I showed you before for rooted trivalent maps and follow through tracking redices during the process. And so for loops, of course, we have nothing to do. There's no redices here. For applications, it's easy to track redices. Either we have an application applied to something, in which case we have no new redex, or we have a lambda applied to something, in which case we have created a new redex. So far it was easy to do. But as one might guess, once you start cutting inside the term, so once you fall into the third case, where we have to cut somewhere inside our term or our map, clearly we can mess up existing radices, we can create new radices in their place, etc. Right? And so I will give you one subcase here, for example. Suppose that I cut on this edge here colored in blue, which forms part of a redex. It's the edge linking an application with its right subchild, which is an abstraction. Then either we cut off to the left, and so I introduce a new application vertex, which I link to the former root, and I have a wire going off to the left, in which case we have destroyed the old redex, but we have created a new redex in its place because we have an abstraction applied to the new fresh variable we introduced. And so overall, we have a net change of 0 in the radices, or I cut to the right, in which case I have the new application, the new variable applied to the abstraction lambda, in which case I have destroyed the redex and I have created no new redex in its place. So overall, I lost the redex. And by a similar kind of case analysis, we consider all the possible kinds of cuts that can happen in a term. And so finally, we arrive to a differential equation which we can pump. And this is a nonlinear differential equation. As we see here, we have some square terms, and it is a partial differential equation because we have derivatives both in z and r. But in any case, by pumping, we can obtain moments of any order. And so, for example, here we have the expectation and the variance for this variable, which counts the number of radices in a closely linear lambda term of size n. And so asymptotically, these are both n over 24. So we should roughly think of something like Gaussianese with a mean of n over 24 for the number of radices. And so as we said, the number of radices was only a lower bound, and it was a crude lower bound because it can happen that I reduce a redex and it reproduces a new one, right? And so if we wanted a better lower bound, our goal would be to refine our counting to track reproducing radices. And so actually there has been a classification, and for this you can see Levy's thesis, of exactly which kinds of radices reproduce, right? So these are exactly the 3 families of radices, 3 general families of radices, whose reduction produces a new redex. And so, for example, this is most clearly seen in the second, the P2 pattern, where we have lambda x dot x applied to lambda y dot t1 applied to t2. And so in this case, clearly we have only one redex in the beginning. We have lambda xx applied to lambda y dot t1. And so if we reduce this, clearly we get, this is an identity function, lambda xx. So we get back lambda y dot t1. So we started with a redex, we reduce it, and now we have a new redex. We have lambda y dot t1 applied to t2, right? And so all three families of patterns here have this property of reducing it, reducing one of their members gives us a new redex back. And so our trick now is to follow through the same process, the same strategy I described for you in the beginning of tracking the creation and the destruction of these patterns during the recursive decomposition I showed you before. And so here again we have the same kind of approach, right? We consider what happens when you cut inside your term. And so, for example, if I have a P1 pattern, which visually you can see it here on the left, either I cut on these 2 purple edges I saw you here highlighted, which destroy the pattern. So these are one of the 2 possible cases, cutting in these edges, or I cut on these other purple edges we have here on the right. So these purple edges are exactly the 3 cases where cutting destroys a P1 pattern, right? And so this is for cutting, and for destroying, and for creating a P1 pattern. To create one, we can either point at this purple edge here and cut to the left so that we create a new P1 pattern, or we cut here, or we have this sub pattern here. We have a loop somewhere applied to some lambda, and we cut off to the left again. And so we see here that for destroying P1 patterns, we did not have to consider anything else, only the number of P1 patterns. But for creating P1 patterns, we now have to consider some auxiliary patterns, these 2 patterns I show you here. And so we need to keep track of some extra patterns. And so finally, for applications, we have to track the creation of P1 and auxiliary patterns. And so this is done in the same manner as before. And we arrive to the following system of equations, where we have Z counting edges, V counting occurrences of our P1 pattern, and U counting occurrences of these two auxiliary patterns. And if you wanted to try the same trick as before to extract the mean, to do a little pumping, we arrive at the unfortunate situation where we have an equation which has derivative both in Z, U, and V. And so this is a bit of a problem, right? We cannot pump if you have all three variables here. Thankfully, though, there's a bijection between terms pointing at one of these auxiliary patterns and terms pointing either at an abstraction or a P1 pattern. So by some kind of magic, a little bit of a bijective magic here, we can replace this Z to the 3 dVs with some combination of du and dz. And so finally, this allows us to obtain a mean number of occurrences of 1/6 for the number of P1 patterns. So this is a bit of a surprise here, because if you consider a huge term, arbitrarily large, then we see that the number of P1 patterns is actually a constant. It's like there's going to be 1/6 of them, which is kind of weird because it seems that it's not that much of a complicated pattern. It should appear more often, right? Anyways, by the same kind of reasoning, we also obtain the mean number of occurrences for the P2 pattern, this lambda x dot x applied to a function, applied to some other term I showed you before. And here we once again get a mean which is constant asymptotically. Of course, here this is not as surprising as the case for P1 patterns, because the P2 pattern actually contains a loop inside it. And if you remember, I showed you in the beginning, one of our results was that the number of loops has a Poisson 1 asymptotic distribution. So we expect this to be anyways some kind of a constant asymptotically. Okay. And so finally, to enumerate P3 patterns, we'll try to do the same trick as before, right? Try to enumerate the P3 pattern together with some auxiliary patterns required for it. But we run into a problem of ambiguity. It can happen that the P3 pattern overlaps with some of its sub-patterns. And so, for example, we have in a situation here, we have P3 pattern highlighted in red, overlapping with the lambda x lambda y T1 auxiliary pattern highlighted in blue. And in this case, unfortunately, pointing and trying to initiate a cut inside a term is an ambiguous process. And so we're not sure whether we're pointing inside the P3 pattern or the lambda x dot lambda y dot T1 pattern. And so this means roughly that we can no longer do an unambiguous decomposition. We have this ambiguity, and therefore generating functionology fails. And we have to revert to a more elementary method of considering directly the expectation in terms of just the expectation of the corresponding random variables, right? And so here we can see that because applications are kind of rare asymptotically, almost no term is an application asymptotically, almost all terms are, like with probability 1, they are abstractions. We can kind of bound crudely the asymptotic contribution of the case of applications, and we only need to consider abstractions asymptotically. And here, by some kind of magic, we see that this expectation linearizes over families of abstractions which are generated by cuts from a fixed term. So if you consider a fixed term and you consider all the possible families that you can generate from, all the possible terms that you can generate from him, this is a family. And so if you consider the random variables cumulated over these families, magically it happens that this expectation linearizes. And so we obtain a system of equations for the random variables counting the P3 pattern together with the two auxiliary ones. And so using this system of equations and the fact that they are linear, we can actually solve it. And so overall, in the end, we get the following lower bound for the number of steps required to normalize n linear lambda term of size n, which is asymptotically 11n over 240 for n large enough. So this is an asymptotic lower bound. And so this essentially was the sum of the expectation for the number of radiuses plus the expectation for the P3 pattern. Everything else was constant. And so during an open problem session of CLA 2020, Noam Zellberger conjectured that the mean for this number of steps is actually n over 21. And you can see we got pretty close. We have 11 over 240 minus 1 over 21 is equal to 0.001, right? So by refining our enumeration, by looking into this P3 pattern more, we can get even closer approximations, right? But of course, these are all lower bounds. To get the asymptotic mean conjectured by Noam, we should look for an upper bound too, and it seems a bit harder to do. In any case, coming back and generalizing a bit this situation, we can count radices by their type of argument. So I'm coming back to the quiz I gave you in the beginning. So I can have three types of radices in general. I can have a lambda applied to a variable, a lambda applied to an abstraction, to another lambda, or a lambda applied to an application. Sorry, this label here should be alpha. And so to give you an answer to this quiz, surprisingly enough, the case that happens more often asymptotically is a lambda applied to a variable. And in fact, the case of a lambda applied to a lambda asymptotically is negligible. It happens over only a constant number of times in a huge term, 1/20. So this is, again, some kind of surprise, because we see these two patterns here are of the same size roughly, but their labels are different. And it seems the labels make a big difference in the number of occurrences. And so to conclude with some open problems, of course, we see here that we have some kind of a weird behavior of patterns in which it's not just the size of the pattern that controls its frequency of appearance, but some kind of a structural property, some kind of property of the labels associated with it. And so one open problem would be to classify these patterns according to the expected number of occurrences, whether it's constant or linear in n. A second kind of possible extension of this work would be to automatize the process of obtaining specifications tracking occurrences of our desired patterns. So we see here that almost all patterns we saw here, radices and these two the two first families, are susceptible to this kind of decomposition based on cuts, right? So perhaps this can be automated. Of course, for the P3 pattern, we saw that this doesn't work anymore. So this kind of automation should take into consideration some kind of structural property that allows some patterns to be decomposed in terms of this cut process and some not. And of course, here perhaps some kind of an approach using differential algebra or something would also aid us to automatize this process and to guess and prove perhaps a specification. And finally, it would be interesting to explore the meaning of beta reductions on maps a bit more and see what kind of connection it has to the knot theory, to the notion of knot trivalent maps, etc. That's it from me. Thank you.
Okay. Okay, thank you for the talk.
Thank you.
Are there questions?
Parses it. Oh, yeah.
No. Ah, yes. Yeah.
Do you hear me?
Yes.
Okay. Yeah, that's good. So the results are very interesting. I was really amazed by those results you get. But I'm also interested by non-linear terms. So
right.
Do you have an idea how this can this be generalized to non-linear terms? And by the way, also it seems that the notion of size you use is connected with linear terms, because I don't think there is other notion of size in the case of linear terms. But in the case of non-linear, you have several notions, and this has influence, for instance, when you give that the asymptotic number of abstraction or the asymptotic number of application. We know that in the case of non-linear terms, it's really dependent of the size. So to summarize, how can you generalize that to non-linear terms?
Right. So as you mentioned, exactly the size notion really affects the statistics, right? So there's some kind of work, for example, for general terms, looking at the how many of them normalize, and by considering different kind of sizes, you can get that almost all terms normalize or almost none normalize. Okay. So the size notion would affect the things a lot. And furthermore, the fact that we focus on the case of trivalent maps, of linear terms, allows us exactly to work with trivalent maps. And so this kind of framework that we have here, it really rests on the use of these decomposition methods with the cutting, etc. So we would have, if we wanted to apply this kind of technique to general terms, to nonlinear terms, we should perhaps find some kind of bijection with some kind of generalized map, non-trivalent map, I mean, and some kind of an analogous cutting process, more general cutting process, to try and apply the same kind of techniques, right? So as it is, this technique that I have here, it only works specifically for trivalent maps and linear terms, because it uses exactly this nice decomposition in the style of TAT. And so to have a more general result, we will have to have a more general bijection.
And perhaps one direction is that the work we have done with my colleague in Serbia is to extend the lambda calculus with operators for duplication of arrays. Because if you duplicate, if you have a non-linear term, you can duplicate terms or the Redex. You can duplicate the argument, and so you have to you may explicitly tell that you duplicate. So you have to expand, and that makes a data structure which is much more complicated.
Yeah, that would be interesting to try and apply the same kind of approach to the more general case where you have explicit duplication, etc.
So, Antoine?
Yes, thank you, Alex, for your talk.
Thank you.
I have a question about the Noam conjecture. So you gave a lower bound that seems a bit larger than Noam conjecture. Do you have a new conjecture then?
No, I think Noam is correct, but I think the lower bound is ever so slightly off. And so the idea is that here actually you can get an even closer lower bound, and it is if I go back here to the family considered by Levy, you can consider here the third pattern, which is alpha whose left subchild is an alpha, whose left subchild is an alpha, whose left subchild is a lambda. You can consider even bigger chains of applications, applied to application, applied to application, applied to lambda, etc. And so by considering even larger chains in this family, you can get even closer approximations, right? You can keep adding terms to this expansion. And so I have an even closer approximation somewhere in my Maple files where it only falls to within 0.00001 away, right? So I think Nom is actually correct. It should be something like n/21. It's just that refining the lower bounds gets tedious very fast. And so what would be better is to perhaps look for a way to deal with all of this directly with one first swoop, and then find a way to have a good lower upper bound also. So an upper bound, a very crude upper bound is of course over 3, which is the number of abstractions in a term. But it's like I don't know any good upper bounds, anyone that get close to it, to n/21.
Well, the point was that the subtraction should be the other way around.
Yes, it's an absolute.
It should be absolute value there, yeah.
Also the next digit is a 7, so maybe it should be a 2 on the slide.
Yeah, approximately, yeah. It looks better if you hide the 7 and you say it's
It's truncated. So
I'm not lying, yeah.
Yes, another question in another direction, maybe?
Yeah.
Yes.
Sorry.
So at the end, in the conclusion, you give 2 either patterns with expected number of occurrences that are constant nor linear in average. So do you have patterns in mind whose expectation is not constant and not
So this is an interesting question. Yeah, I kind of say that I kind of imply that the only cases are constant or linear, but I don't know, maybe there's logarithmic number of occurrences for some patterns. But in fact, from like all the patterns I have studied, and so have done a pretty exhaustive enumeration for a lot of little patterns of the form application applied to an application, all of these kind of things. It seems that they all fall within the 2 beings of either being constant or 0, but still 0 is constant, or linear in n. I didn't find anything logarithmic yet. So that would be an interesting thing to try to see if there's like any kind of other possible behaviors, but or if not, to try to prove that the two possible behaviors are either constant or linear.
Okay, thank you very much.
Thank you.
Okay. Further questions? And in the chat? No. No. So then just a final remark to Antoine's question. I think that we can, according to what we are observing in combinatorial structure, it's maybe unlikely to have a logarithmic in between, because I would expect that the one that are constant are kind of corresponding to a Poisson law, and the other ones where we have a linear number of occurrences will be a normal limit law. Though there are no proofs of this kind, but this is my expectation. And as the Poisson is normally the kind of boundary case, the borderline case where the normal starts to degenerate. So then we have normally normal Poisson and degenerate, and the expectation follows also a pattern which corresponds to this. So linear, constant but positive, and zero. So I would not expect to have a log n somewhere here in this kind of pattern theory.
Okay, maybe a last question related to this. So Alex, you said, this is Martin. Alex, you said that sometimes it was zero.
Yeah.
You mean it tends to zero, right? Or
yeah, asymptotically it's zero, yeah.
So maybe, do you know how quickly it goes to zero?
No, this is the problem with all of these kinds of pumping arguments, is that you only get the asymptotics, and you like, I don't know how to get speed of convergence for this kind of, we don't have like Berry-Esseen and this kind of tools from the analytic side. So it seems it goes fast, because anyways, if you plot it, it goes to zero pretty fast, but this is not mathematics, this is physics. But it seems pretty fast. like 1/n or something. It's pretty rapid. Or even n square, and yeah.
So then thank you again, Alex, for the nice talk. And we have a break until 10:45, I would say, half an hour break. So we start 10 minutes later with the next talk.
Thank you, Alex.
Thank you.
Thank you.